Dear friends, good morning. My name is Pankaj Tumka. Today, we will be discussing about equivalence of Kelvin Planck and Clausius statement. In last lecture, you have studied what Kelvin Planck and Clausius statements are. Now, Kelvin Planck statement acts as the base for any engine, and Clausius statements act as a base for any refrigerator or heat pump. But these two statements, if you view, you will say that they are two different statements. They are not the same. But we can prove that they are the same. And this can be done when we can prove that the violation of one violates the other. So let us consider a case. Consider a case in which that we have a reservoir at temperature T1, another reservoir at temperature T2. And between these reservoirs, a heat pump is working. And it is working such that it is taking heat of Q1 amount from T2 reservoir and delivering heat Q2 amount to the reservoir number 1, that is T at temperature T1. Now, if you look this, that it seems to us that this is the violation of a Clausius statement, and it is true. Why? Because there is no work interaction involved here. So we will be proving that as this is the violation of Clausius statement, so we will be proving that this violation leads to the violation of Kelvin Planck statement. So let us consider a heat engine working between the same temperature limits, and it is taking Q2 amount of heat, the same amount of heat from this reservoir as the amount of heat which is rejected by this, and this is rejecting some amount of heat, say it is rejecting Q3 and developing some work. Now, if you look the situation very closely, what is happening? The heat engine is taking the same amount of heat as rejected by this heat pump. So it seems to us that there is no need for this thermal energy reservoir. That simply means we can transfer this heat to the heat pump. So what is happening basically? This hole is forming an engine which is developing work in a cycle, and this is in contact with a single energy reservoir, that is violation of Kelvin Planck statement. So we have just proved that the violation of one, that is Clausius statement, is a violation of Kelvin Planck statement. We can also do it other way around. Let us consider a thermal energy reservoir at temperature T2, another thermal energy reservoir at temperature T1 and T2, and an heat engine is working between these such that it is taking heat Q1 and delivering work W2, but in turn it is not rejecting anything. Now consider a heat engine, consider a heat pump working between the same temperature limits, and it is doing what? It is taking Q2 amount of heat from here and delivering some amount of heat, say Q1 plus Q2 to this reservoir, let us say. Then to drive this heat pump we will be requiring work. From where this work will come? This work we can give to this heat pump. So together what is happening? This is forming a heat pump where it is taking heat from a lower temperature reservoir and delivering heat to a higher temperature reservoir, which is violation of Clausius statement. So we have seen that the violation of one statement leads to the violation of other. That is, if Clausius statement is violated, Kelvin Planck will automatically get violated, and if Kelvin Planck is violated, then Clausius statement will get automatically violated. So hence these two statements are not independent statements. These are the same, that is violation of one leads to another and violation of another one leads to the violation of first one. Now, what is a reversible process? What is a reversible process? A reversible process is one which, when reversed, which when brought back from its second state to its primary state, the effect which it has produced in going from state 1 to 2, let us say this. This is a process performed by system from 1 to 2. And if I am bringing it back from 2 to 1, the changes which the system has made onto its surrounding when coming from 1 to 2, they all will be reverted back. And in a nutshell, what will happen? What can be said? We can say that the system has not done any change in its surrounding. That is, the whole effect has been wiped out. So if this is happening, then we will say that the process performed by the system is a reversible one. Or in other words, if the system leaves no trace for its existence, no trace of its path, that is, the process had never occurred, then that is a reversible process. So, when this reversible process is possible? This is possible only when there is a infinitely small, that is infinitesimal gradient. We always know that any system performs an action when there is a finite gradient. For example, if there is a finite gradient in temperature, then heat will flow. If there is a finite gradient in pressure, then the work will be flowing from the system to the surrounding or from the surrounding to the system, vice versa. So this infinitely small temperature gradient will lead to a reversible process. So what is the characteristic of a reversible process? It is a very, very slow process. That's why quasi-static processes are sometimes called as reversible processes. So if the process is very, very slow and occurring at a very small gradient, then we can say that process is approaching a reversible process. Even if you have a finite temperature gradient and you are allowing that process to occur very slowly, that means the time taken in that process is very large, then that process can be thought of as a reversible process. Why? Because we are not allowing that process to occur with its natural rhythm. We are playing with its rhythm, or ultimately we are playing with the time. So time is a very crucial, very important parameter in deciding whether a process is a reversible or an irreversible process. If the time taken by a process is very large, so then that process can approach as a reversible process. So time is very, very, very important parameter in defining a process, whether it's a reversible or an irreversible. On the other hand, if the time taken is very small, then the process will be very fast, and hence it does not qualify to be a reversible process. So what are the causes of irreversibility of a process? Irreversibility of process is caused because of many things, and let us discuss them one by one. The first cause is the lack of equilibrium. The lack of equilibrium between the system, surrounding, the lack of equilibrium within the system, and these are because of finite gradients. Finite gradients of what? Finite gradient of temperature, finite gradient of pressure. So let us discuss first finite gradient of temperature. What this finite gradient of temperature is doing, or how this finite gradient of temperature is making a process irreversible. So let us consider we have a thermal energy reservoir A and a thermal energy reservoir B. A is at higher temperature than B, that is T1 is more than T2. What will happen? Heat will naturally flow from this higher temperature to this, that is Q A to B. Now you do one thing. To prove that this heat transfer is an irreversible process because of this finite temperature gradient, let us argue in this fashion that let QAB is reversible. If I can prove that this is wrong, then ultimately we will be proving that QAB is irreversible. Let us say initially that this is reversible. Let us see what happens. And install an engine such that it takes this much amount of heat to operate in a cycle like this. Now, as this is reversible, so I can revert this. I can reverse the direction of this. And this engine is working in such a fashion that the amount of heat, this QAB, is same in magnitude as this. So if I am reverting it, so it will not be QAB anymore, it will be QB from A, B to A. So what is happening? The magnitudes are same, so I can transfer this heat directly to this engine. So you can see this engine is developing work, so I can omit this. So I can say this is my engine, this is developing work, rejecting heat, B at T2, this is heat transfer and directly transferred to this engine. So this engine is in contact with a single thermal energy reservoir, which is not possible. Why? Because of violation of Kp or Kelvin Planck statement. Hence, we can say that the heat transfer which is occurring because of finite temperature gradient is irreversible. So if at all somebody wants to make a reversible heat transfer, then what he has to do? He has to reduce this temperature gradient to an infinitesimal temperature gradient, that is infinitely small temperature gradient. And for that infinitely small temperature gradient to transfer heat, the time required will be infinitely large. And that infinitely large time will make that process, or will qualify that process as a reversible process. But in reality, in nature, every process of heat transfer is irreversible because they all occur with a finite temperature gradient. Now let us consider a different case. Again, lack of equilibrium, but lack of mechanical equilibrium. Let us consider you have a chamber in which you have a gas, on another side it is vacuum. Now you know, when you remove this partition or when you puncture this, let us say this is adiabatically sealed, no heat can interact with, this system cannot interact with surrounding or surrounding with system. So if you puncture this partition or remove this partition, then gas will rush to fill the vacuum. But the reverse process is not possible. We know gas cannot itself come to this smaller portion and make this partition vacuum again. This is not possible. So let us say this process in reverse direction is possible. Let us say, that is, gas can come from this end to this end, accumulate here and make this partition vacuum again. Let us say this is possible. This is A, this is B. So let us consider an engine working between these two. So the gas, and I am assuming that this thing, that gas can move from B to A, making this B again vacuum. That means the transfer of gas from B to A is reversible. That means motion from here to here, this is reversible. Engine is developing work. How? This gas is coming here, working on this engine, transferring work to atmosphere, and then coming to this portion. And in this portion, what I am doing, I am transferring. Now the moment gas occupies this will not be a vacuum anymore. So I am transferring heat from a heat source. I am transferring heat to it so that its internal energy again rises, and as it rises, it will move from here to here and making this again a vacuum. So what I am doing here in this, if you look this in its totality, I am forming an engine which is working with a single energy reservoir and developing work continuously in a cycle. This is again violation of Kelvin Planck statement. Hence, the free expansion, this free expansion is a irreversible process, is not a reversible process. Now, the irreversibility of process can also be caused because of dissipative effects. Now, what are dissipative effects? Dissipative effects are like churning of a fluid by a paddle wheel, or when you apply brake, then the kinetic energy of the wheel get converted into friction, is consumed by friction and get converted into heat. So let us consider that case. You have a wheel and you have a brake. This is rotating like this. So friends, if you neglect this space, or say that this space is very small when this brake is moving in this direction, so that no work can be done in terms of displacement, then the whole of the kinetic energy of this brake will converted into the kinetic energy of this wheel will get converted into internal energy of this brake. And the reverse of this is not possible. If you supply heat to this brake, this wheel will not start rotating. So this is an irreversible process. But how to prove that this is an irreversible process? Let us say that this is a reversible process. Then what will happen? Whole of the kinetic energy will get converted into the internal energy of brake. The internal energy, that is temperature of this brake, will rise. And as this is a reversible process, so let us say that this is losing heat to atmosphere. Now again, we are supplying heat to this brake. We are supplying heat to this brake from some, because of which its temperature rises. And as I said that this is reversible, that is heat can be converted into kinetic energy somehow. So this will start rotating. And if I connect a pair of weights to it, so pair of weight will rise. That means this whole system will be doing some work. Again, we have a thermal energy reservoir. We are making an engine which is working with this thermal energy reservoir only and producing work. Again, violation of Kelvin Planck statement, which is not possible again. So hence, the dissipative effect is not possible. And this is very, very general thing to look into. How? Like you all know, if you rub your hands very fast, the temperature between your palms will rise. And if you heat your palms with the help of some external agency, your hands will not start moving. It's not possible. So, friends, dissipative effect or dissipation of energy by friction is always an irreversible process. It is not a reversible process. So the thing which is important here is to make a process reversible, you have two things to keep in mind. The first one is that the gradients of anything, whether it is temperature or pressure or anything, the gradient has to be infinitely small for the process to be reversible. And the second important, very important thing is that the dissipative effect should not be there. Friction should be completely absent. So here we define a perpetual motion machine of third kind. You must have read about perpetual motion machine of first kind, second kind. And second kind is the violation of Kelvin Planck statement. What is perpetual motion machine of third kind basically? It is a machine. What is a perpetual motion machine of third kind? It is a machine which is working. Let us say that we have a frictionless surface. This is frictionless surface. So if I give motion to it, what will happen to this roller? It will roll and roll and roll, and it will never stop, because the agency which is stopping it is friction. So if we can make a machine which can roll over for infinity, then that is a perpetual motion machine of third kind. That is the continual motion of a moving device or movable device in the complete in the complete absence of friction is known as perpetual motion of third kind, and the machine which is performing this action is known as perpetual motion machine of third kind. Sorry. Now come to Carnot cycle. Lot many people pronunciate this as Carnot cycle, but in reality it is not Carnot, it is Carnot cycle. The pronunciation is Carnot cycle. So what is a Carnot cycle? Carnot cycle is a combination of four processes. What are those four processes? Two isothermal and two reversible adiabatic. If we plot this onto a PV plane, it will be like this. This is one isothermal, this is adiabatic, this is another isothermal, and this is adiabatic. So this is the case 1, 2, 3, and 4. This is a Carnot cycle. And engine which works on this cycle is known as Carnot engine. This is the idealist cycle which we can think of. Idealist and possible. Possible in sense of idealism, but not in sense of reality. We cannot produce this cycle in reality, but we can think of this cycle. How? Q1 is transferred to this cycle in isothermal process. This cycle performs work in reversible adiabatic expansion. There is a heat loss in isothermal process, and then there is again a work transfer to the cycle in this reversible adiabatic compression. So you have Q1 plus minus Q2 as the net heat transfer to the cycle, and W1 minus W2 as the net work transfer from the cycle. And this is very well possible because you have two thermal energy reservoirs which are supplying heat at T1 and T2. So friends, if we talk of this cycle, so the efficiency of this cycle will be net heat transfer to that of heat input, and net heat transfer is same as network transfer is same as net heat transfer. So this will be Q1 minus Q2 by Q1, which is simply 1 minus Q2 by Q1. So in schematic sense, we can say that we have an engine which is a reversible engine. It is taking heat from a reservoir at temperature T1, rejecting heat to reservoir at temperature T2. and in turn doing some work. And the cycle which is performed here is a reversible cycle, because every process in this cycle is a reversible cycle. We can revert it back. Now, if you want to reverse this, as this is a reversible cycle, it can be reverted very well. Reverted. This negative inverse means I am reverting it, or some authors used to like write this thing like this. They are the same. Or this. So this is my cycle. Now I am reverting it, making this in reverse direction. So this is T2, this is T1, this is T1, this is Q1, and this is Q2, and this is W net. So you see, in reverting the cycle, what you did, you have just changed the directions of the heat or work, but the magnitude remains the same. So this is the thing which we have discussed. What we said that what is a reversible cycle? A reversible cycle is that cycle which is performed in such a way that when the system is brought back to its initial state, the effect which the system has created in coming in the forward direction has been wiped out by the system in moving back. So reversible cycle is this. That is, we have reverted every direction, keeping the magnitude same. The net impact on this universe is 0. So this is my reverted cycle. And this, if this is an engine, if I am saying that this is an engine developing work, so this can be thought of as a reversible heat pump or a refrigerator. Now here in this respect, there is one very, very important theorem. That theorem is known as Carnot's theorem, the Carnot's theorem. And what this Carnot theorem says? It says if you have let us say two engines, EA and EB, and they are taking, let us say, same amount of heat, Q1 and Q1, and they are rejecting some amount of heat, say Q2 and Q3. This is developing some work WA, and this is developing some work WB. This is at temperature T1, this is at temperature T2. That means if you have two engines which are working in a cycle, and working in a cycle such that they are in contact with the same thermal energy reservoir, or they are at the same temperature difference level, then the engine which is reversible will be having higher efficiency in comparison to the engine which is irreversible. Let us say that engine A is reversible and engine B is irreversible. So we have to prove that engine B's efficiency will always be less than engine A's efficiency. So again we will start with the negative analogy. Let us say that engine A is less efficient than engine B. Then engine A is a reversible engine. So revert this and see what happens. Reverting it, this is my engine, this is my T1, this is T2, this I am reverting engine A. So what will happen? All the heat and all the energy interactions will get reverted. So this is what? This is WA, this is my engine B, this is Q3, this is Q1, and instead of writing WB here, I will write it here, WB. As this is reversible engine, so I reverted it. Now look very carefully. A very strange thing is happening. Let us say, as we have started with the thought that efficiency of engine A is less than efficiency of engine B. That means WA by Q1 will be less than WB by Q1. Why Q1? Because initially what I said that these two are equal. So that simply means work what WA is less than WB. So this engine will be producing less work than WB. So in reverse direction, this work will be less than this. So what I can do is, I can transfer this WA from this only, and the balance, that is WB minus WA, will be the net work from this particular assembly. So what I am doing, I am making an engine which is working in a cycle and developing a work WB minus WA, and this heat can be transferred here and interacting with only single thermal energy reservoir. That is violation of Kelvin Planck statement. Hence it is true that if you have many engines working between same thermal energy reservoir, then only that engine which is reversible will be having the highest or maximum efficiency. And its corollary, what it said, it says that efficiency of all reversible heat engine operating between the same temperature level is the same. For example, if we have, let us say, A, B, C, D, and they are interacting with two thermal energy reservoirs T1 and T2, developing some work, then if they all are reversible engine, then they all will be having same efficiencies as they are working under same temperature limits, or they are working between same thermal energy reservoir. So this simply means, in general sense, that these all engines, as they are different engines, and their working fluid will also be different, and their efficiency is same. That means that if reversible engines are working between same temperature limits, then efficiency becomes independent of the nature or amount of working substance which we are using in this cycle. So efficiency, so in general sense, efficiency of a reversible engine depends on what? On T1 and T2. That is, depends on the temperature limits on which that engine is working. This is a very important conclusion which we have derived from Carnot's theorem. And this becomes the foundation for the absolute thermodynamic temperature scale, for the development of absolute thermodynamic temperature scale. Let us see what is that. Consider a engine 1. This engine is working between temperature limits T1 and T2. It is taking heat from this and delivering heat to this, and in turn developing some work. And another engine, E2, is taking same heat from this, that is Q2, and delivering some heat or rejecting some heat to the another thermal energy reservoir T2, and in turn developing some work. So just now we saw that efficiency of an engine, that is 1 minus, if I consider engine number 1, then that will be Q2 divided by Q1, and this efficiency will be a function of T1 and T2, that is temperature limits on which this engine is working. So what I can write is Q2 by Q1 will be 1 minus function T1 T2, or Q1 by Q2 is 1 divided by 1 minus function of T1 and T2. So this Q1 by Q2 is a function of T1 and T2, and let us say this function is some T1 and T2, like this. So if we consider engine 2, engine second, then what I can say here, Q2 is, this is Q3, sorry, Q2 by Q3, this will be again a function of T2 and T3. So if we combine these two engines and make another engine which is taking heat Q1, transferring heat Q3 and developing some work, then what I can say from here that Q1 by Q3 will be a function of T1 and T3. So friends, if we consider this, that is Q1 by Q2, we can write this as Q1 by Q3 divided by Q2 by Q3. What is Q1 by Q3? It is a function of T1 and T3. And what is Q2 by Q3? It is a function of T2 and T3. But what is Q1 by Q2? Q1 by Q2 was originally a function of T1 and T2. And this is represented as this ratio. So Q1 by Q2, which is a function of T1 by T2, is coming out to be this ratio. And in this ratio, in numerator you have T3 and in denominator you have T3. So this T3 will drop down as this Q1 by Q2 is function of T1 and T2 only. So I can write this function in some other form like this. Let us say zeta. So this zeta is a function of T1 and here it is a function of T2. So our expression, this expression has been converted into this, that Q1 by Q2 is simply a ratio of these two functions which are functions of T1 and T2. So Lord Kelvin did what Lord Kelvin developed, and Lord Kelvin said that this function we will consider as absolute thermodynamic temperature, and that's why we used to write this as T1 and T2. What is absolute thermodynamic temperature? It is temperature in degrees Celsius plus 273.15, that is Kelvin. So this Q1 by Q2 is equal to T1 by T2 becomes a basis for temperature measurement even, and this becomes a basis, or this becomes a representative of a reversible heat engine. If an engine is reversible, then this heat transfer ratios will be equal to the temperature ratios from which these heats are getting transferred. So how it becomes a measure of temperature? Let us say that we have a system at temperature T1 whose temperature is to be measured, and we are inserting an engine here, and this engine is rejecting heat to a temperature T2. What is this T2 here? This T2 is not an ordinary temperature. This T2 is basically the temperature of triple point of water, because this is rejecting heat to triple point, water at a triple point. So if this is Q1, this is TT, this is W, so this Q1 by QT will be equal to what? T1 by TT. So this T1, that is temperature of this system, will be TT Q1 by QT. What is TT? It is 273.15 Q1 by QT. And we know this is what? We have seen this. If we say that we are measuring temperature with the help of a mercury and glass thermometer, and we are using a single fixed point scale, then this fixed point, that is a triple point, then that will be L by LT, that is temperature measurement with the help of mercury and glass thermometer. Here the thermometric properties are what? Here thermometric properties are the length rise in the capillary tube of that mercury and glass thermometer, and here it is very similar to that. So we can think that this heat as the thermometric property for the measurement of temperature. This is not all what we have to say for this temperature measuring scale, because we are developing a new type of scale here, and this scale can be having different graduations, and it must have some definite 0 point also, because this is a scale. So if you think in this fashion, or if you say that I want to develop a scale where 0 is there, where is that 0? So if you have an engine which is working between, say, temperature T1, like this, engine 1, rejecting heat, to some temperature T2, rejecting heat, this E2 gained by rejecting heat, T3, it is Q1, it is Q2, it is Q2, it is Q3, and in doing so there will be an engine which is developing some work, and that work will become exactly equal to the amount of heat that engine has gained, and in doing so it will be transferring zero amount of heat to a thermal energy reservoir whose temperature is absolutely zero. So what you are doing here is you are forming an engine where you are taking energy from T1 and delivering zero amount of heat to a temperature at absolute zero. Hence, you are forming an engine which is working with a single fixed reservoir. That is the violation of Kelvin Planck statement. Hence, this absolute zero temperature is not attainable. You cannot attain this absolute zero temperature in finite number of cycles, or even in infinite number of cycles, because if you can do this, then you will do what? You will violate Kelvin Planck statement. And this is basically the third law of thermodynamics, and it says that it is impossible by any process, any means any process, no matter, it will not matter how much idealized that process is, but it is not possible to reduce any system to the absolute zero temperature in a finite number of operations. So what is third law of thermodynamics? Third law of thermodynamics says that the attainment of absolute zero temperature is not possible. You cannot attain a 0 Kelvin. Not possible. So just using the thing which we have derived is, and summing. Now consider that this is my engine, reversible engine, taking heat Q1, delivering heat Q2 toward thermal energy reservoir T2, taking it from T1 and developing some work. So efficiency will be 1 minus Q2 by Q1. So as you know, you have just seen from the development of Kelvin temperature scale that Q2 by Q1 is same as T2 by T1. So this will be 1 minus T2 by T1. So if this engine, as this engine is a reversible engine, so if I can revert it, so the heat interaction will get reverted. That means this is Q1, this is Q2, this is T2, this is T1, and this is the amount of work which I am doing on it. So the COP of refrigerator, if I am looking this as a refrigerator, so desired effect will be this, that is Q2 by W. And what is W? It is nothing but Q1 minus Q2. So if I divide this whole equation by Q2, I will get 1 upon Q1 by Q2 minus 1. And what is Q1 by Q2? It is T1 by T2. So 1 by T1 by T2 minus 1. So it will be nothing but T2 upon T1 minus T2. Similarly, efficiency of a heat pump, which is desired effect upon work done. What is the desired effect in case of heat pump? It is Q1. So it will be Q1 divided by Q1 minus Q2, dividing by Q2. It is Q1 by Q2 divided by Q1 by Q2 minus 1. So Q1 by Q2 is T1 by T2 for a reversible one. So this will be T1 by T2 divided by T1 by T2 minus 1. Taking LCM, it will be T1 by T1 minus T2. So these are the efficiencies and COPs of a reversible heat pumps and engines. So friends, before winding up this lecture, I will be once again focusing on irreversibility. So how many types of irreversibilities are there? Basically, 2 types. First one is internal irreversibility and second one is external irreversibility. What is internal irreversibility? Internal irreversibility means the irreversibility which is coming into picture because of friction, internal dissipative effects. And what is external irreversibility? Which occurs at this boundary of a system. That is, Because of boundary phenomena. And you know, heat transfer is a boundary phenomena. So, whenever you are transferring heat to a system at the finite temperature gradient, that simply means that is a irreversible cycle, or you are bringing irreversibility to the system because of that external heat transfer. And this one is, and this type of heat interaction or this type of energy interaction is known as external irreversible energy interaction. Hope that you have understood the things. Thank you very much for watching. Please do subscribe if you liked my video.